Hi everyone. In this lecture we're going to talk about the dot product. If you have two vectors in Rn, u and v, then the dot product of u and v is calculated by multiplying the entries of u with the corresponding entries of v and then adding everything together. For example, if u is 1, 2, 3 and v is 4, 5, 6, then to compute u dot v you would multiply 1 times 4 and then 2 times 5, and then 3 times 6, and then add all of that up. And the result is 32. Great. But what does it mean? Well, the dot product is really important because the dot product is the key to geometry. So what does that mean? Well, geometry has to do with measures of size, things like length, distance between points, angles, stuff like that. So let's start by talking about length. So suppose I asked you to find the length of a two-dimensional vector. You probably know how to do that. It's the square root of v1 squared plus v2 squared. And usually we'll denote the length of a vector by these double absolute value signs. Now here's the thing. Do you remember there was a time when I told you that everything in linear algebra can be expressed in terms of addition and scalar multiplication? Well, it turns out that's not really true. The length of a vector cannot be expressed in terms of addition and scalar multiplication. After all, if you just do addition and scalar multiplication, you're just going to get linear combinations. You're never going to get squares. So what that means is that we need to add the dot product to our repertoire of basic operations in linear algebra, so we can make sense of notions of length. And when we do that, we can interpret length in terms of the dot product. The length of v is the square root of v dot v. And that's not just true for two-dimensional vectors, that's true in all dimensions. Now, let's say we have two vectors and we want to ask what's the distance between those two vectors. And specifically what I mean by distance here is the distance that's drawn in yellow in this picture. Well, when you subtract one of these vectors from the other, you actually get a vector that represents that edge between u and v. So in this picture I've drawn v minus u, but if I had u minus v, it would just be the same thing with the arrow going in the opposite direction. So this means that the distance between u and v is just the length of v minus u. And since we've already established that length can be expressed in terms of the dot product, it follows that distance can be expressed in terms of the dot product. All right, so then the next thing is angles. And the most important thing to know here is that if you have two vectors u and v, then u dot v will be equal to 0 if and only if u and v are orthogonal, which means that they're at right angles to each other. They're perpendicular. And here's why this is true. It basically comes down to using the Pythagorean theorem. As we just saw previously, u and v form a triangle where the third edge of the triangle is v minus u. According to the Pythagorean theorem, this triangle will be a right triangle exactly when the length of u squared plus the length of v squared is equal to the square of the hypotenuse, which in this case would be the length of v minus u squared. Now, we can write this equation out in terms of the dot product. And the cool thing is because all the lengths are squared, the square roots all disappear in the equation. And so the equation is just u dot u plus v dot v equals v minus u dot v minus u. Now, there are a couple of properties of the dot product that we need to use here. These are just algebraic properties that are fairly straightforward for you to verify, and so I'll leave it to you. But one of those properties is that you can distribute over the dot product. So when we have v minus u dot v minus u, we can expand that out in the same way that we're used to expanding out products. And so when we do that, we get v dot v minus 2 times u dot v plus u dot u. And one more thing that we used here was the commutativity of the dot product. U dot v equals v dot u. So we were able to combine those two terms together to get 2 times u dot v. And now there's some cancellation that can occur. You can cancel the u dot u's and the v dot v's on both sides of the equation. And what you end up with is a 0 on the left-hand side and minus 2 times u dot v on the right-hand side. And then, of course, you can divide by minus 2, and you just get the equation that u dot v equals 0. So just to summarize, what we just showed is that the triangle formed by u and v will satisfy the Pythagorean theorem exactly when u dot v equals 0. And of course, satisfying the Pythagorean theorem means that that triangle is a right triangle. Now, there's an even better version of the result we just proved, which gives us a way to find the angle, even if it's not a right angle. But it requires you to remember something that you've probably long ago forgotten, so I'll remind you of it. It's the law of cosines. So what happens in the law of cosines is that you have a triangle, and it can be any triangle now, it doesn't have to be a right triangle. So you label the three sides of the triangle, A, B, C, and you let theta be the angle between A and B. Then the law of cosines says that c squared is a squared plus b squared minus 2ab cosine theta. In the case where theta is a right angle, then the cosine of theta will be 0, and you'll just get the Pythagorean theorem. So the law of cosines really is a generalization of the Pythagorean theorem to triangles that aren't necessarily right triangles. So now let's go back to vectors, and let's look at the triangle that's formed by the two vectors u and v. And let's say that the angle between u and v is theta. Then, according to the law of cosines, the length of v minus u squared should be equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times the cosine of theta. And then, just like what we did with the Pythagorean theorem, we can rewrite these square lengths in terms of dot products. I could also rewrite the other lengths in terms of dot products in that last term, but I don't want to mess around with square roots, so I'm just going to leave that the way it is. And then, again, just like what we did with the Pythagorean theorem calculation, we can expand the parentheses on the left, and then we can cancel the u dot u's and the v dot v's on both sides. And then if we also cancel those minus 2's, then we end up with the equation u dot v equals the length of u times the length of v times the cosine of theta. So to understand what this means in terms of the angle, it's helpful to just think about how the cosine function works. As I mentioned earlier, cosine of theta equals 0 when theta is a right angle. But then you can see from the graph that cosine of theta is going to be positive when the angle is acute and negative when the angle is obtuse. And so that tells us something about the sign of the dot product. The dot product will be positive when the angle is acute and negative when the angle is obtuse. And so here are a couple of pictures where you can just look at the vectors and you can see whether the dot product is going to be positive or negative based on whether the angle is acute or obtuse. So one important application of the dot product is to orthogonal projection. You remember at the beginning of the semester, we talked about orthogonal projections. We talked about how those are linear transformations. But you'll also remember that they felt kind of complicated back then. And part of the reason why is that we didn't have the dot product, and so we didn't have a good way to get a handle on the geometry, in particular, the notion of orthogonality, but now we do. So let's say you have a line L through the origin, and then you have a vector x. And you'll notice that I didn't draw any axes here, and part of the reason is that I want to emphasize that the argument that I'm about to make is valid in any number of dimensions. It's not just in 2 dimensions. And so you could imagine this picture sitting inside of 3 dimensions or 4 dimensions, and everything would work equally well. Okay, so the way the orthogonal projection works is that you drop a perpendicular down from x onto L, and then the point on L that you reach determines this vector, the orthogonal projection of x onto L, and this is the notation for that, this proj sub L of x. Well, hopefully, after seeing the earlier part of this lecture, your instinct is to draw a vector that represents the third edge of this triangle. A lot of books will refer to this vector as the orthogonal component of x with respect to L, and denote it like this, as orth sub L of x. But that triangle means that there's an equation that relates all of these things. X is the sum of the orthogonal projection and the orthogonal component. And you could rewrite this equation as saying that the orthogonal component is x minus the orthogonal projection. Okay, so now let's let u be a vector that spans L. I could draw u on the picture, but the picture is already a little bit cluttered, so I'll leave it alone. But what this means is that every vector that's on L is a scalar multiple of u. So in particular, we can write the orthogonal projection of x as c times u. And then we can substitute that into the above equation for the orthogonal component and get that the orthogonal component is x minus cu. But there's something else that we know, And that's that this orthogonal component is orthogonal to L, and so it'll be orthogonal to any vector that's on L. In particular, it'll be orthogonal to U. And we can express that property as a dot product, that the orthogonal component dotted with U is equal to 0. From there, we can substitute in x minus cu for the orthogonal component, and then we can distribute the dot product over the parentheses. And then we can solve for c. C is x dot u divided by u dot u. And then we can take this and plug it back into the expression for the projection. And we get this formula, which is the formula for the projection of x onto L. So I bet many of you have seen this formula before in other classes because it comes up in a lot of applications. For example, in physics, you might have a force that points in one direction, but then an object that's constrained to move in another direction. So if you want to know how the force is actually contributing to the motion of the object, you would take the orthogonal projection of the force onto the direction of motion. Or another example is if you have solar panels, you would ideally point them so they're facing directly at the sun. But if not, then the effectiveness of the panels is diminished by the cosine of the angle. And that's because the formula for the flux of the solar energy involves an orthogonal projection, and the orthogonal projection formula involves a dot product, and the dot product is related to the cosine of the angle. I know, it's crazy, isn't it? Okay, so here's an example that uses this formula. Suppose we want to find the matrix that orthogonally projects onto the line y equals 2x in R2. So here is a picture of the line, and the first thing that we're going to want to do is find a vector that spans that line. So I'll pick 1, 2, but you literally could pick any point on that line except for the origin. And then, to find the matrix, we need to find out what happens to E1 and E2. So let's start with E1. So we'll just use the formula that we found in the previous slide for the projection of E1 onto L, and just put in the numbers for U and E1. And then we can calculate the dot products in this formula. And the dot product in the numerator is 1, and the dot product in the denominator is 5. So we get 1/5 times the vector 1, 2. And so that means that 1/5, 2/5 will be the first column of the matrix. And then to get the second column of the matrix, we just do the same thing, but for E2. And this time, the dot product in the numerator is 2, and so we get 2/5 times the vector 1, 2. And so we end up with 2/5, 4/5 as the second column of the matrix. And so that's it. We've got the matrix. So I think you'll agree that the dot product really makes it much easier to find these orthogonal projection matrices.